In this video, we are going to learn about the issue of reproducibility in science. If you cast your mind back to the video where I explained the scientific method, you'll recall that we start with a hypothesis, then gather evidence to test it, and then return to our hypothesis. There's another point to bear in mind here, which is that theoretically, your experiment should be repeatable by anyone. This is what we mean by reproducibility. You would be justified in asking, do scientists actually make sure their experiments can be reproduced? You might be surprised to learn that the answer is not very often. This survey found that a third of scientists did not have procedures in place to make sure that their experimental results could be reproduced, and most of the rest had only started doing so in the past few years. There are a number of reasons why reproducibility has been and continues to be ignored, and much of the blame is simply a byproduct of the way that incentives are structured in professional science. Let's take a tour through how science is done in the 21st century, and see how reproducibility can become a low priority. As a scientist, you have to raise money to pay for your research, to pay salaries, buy supplies, buy equipment. Scientists get this money by applying for grants from funding sources, such as the National Science Foundation and the National Institutes of Health. However, there are a lot of scientists and not much money to go around. Funding tends to be allocated towards exciting new ideas, rather than towards reproducing old ideas. Then there's the issue of data sharing. Historically, scientists have not shared a lot of their data. Partly this was because there were not good ways to share data until recently, but the lack of sharing is also because science is competitive. The data that you have spent time and money collecting allows you to write research papers and apply for more funding, which in turn will affect whether you get hired and promoted. So although good science would have us share our data freely and openly, the structure of the profession incentivizes scientists to hold on to their data so that only they can work on it. In fields such as medicine and the social scientists, where you have data on real humans, there are also privacy concerns regarding sharing data. We all want cures for diseases, but none of us want our personal medical data released openly on the internet. There's also a lack of interest in replication. People usually choose science as a career because they're interested in discovering new things, not because they want to spend their days trying to reproduce old experiments. When a scientist has discovered something worthy of communicating to the world, they publish it as an article in a journal. These articles are how scientists get evaluated. When George Mason hires a new scientist, one of the most important things they consider is how many publications that scientist has, and how prestigious are the journals that each of those articles was published in. Unfortunately, these prestigious top-tier journals only got that way because they publish groundbreaking new science, and not replication studies. So as a young scientist trying to get a job, you might face a conflict between doing more replication work or trying to do something new with less replication that will get published in a top-tier journal. Unfortunately, only one of those activities will look really good on your CV. And then, even if you decide to reproduce somebody else's experiment, you might have a hard time doing so, because experimental procedures are often poorly documented. These vague methods mean that it is often impossible to exactly replicate the conditions of the original experiment. All of these factors have led to a problem in science called the reproducibility crisis. As these graphs show, a lot of scientists have struggled to reproduce their own work, let alone somebody else's. Even more worrying, very few had tried to publish their replication attempts. In recent years, there have been several high-profile attempts to reproduce scientific results. This study, for example, tried to reproduce the results from 100 psychology experiments, but was only successful in about a third of those cases. Now this might seem like just numbers, but publishing incorrect science can have major repercussions. I want you to cast your mind back to 2012. The US was still trying to pull itself out of the recession brought on by the 2008 housing market crisis, but even after 4 years, the recovery was sluggish. President Obama was running for re-election against Mitt Romney, and a key issue in their debates was whether Obama had handled the recovery correctly. When he had assumed office 4 years earlier, Obama had injected a huge amount of money into the economy to prevent it from collapsing, and to try to prevent an even worse recession. Of course, the government didn't have a huge amount of money sitting around, so they'd increased the national debt to be able to do so. In the middle of all this, two Harvard economists, Reinhardt and Rogoff, had published this study where they showed that increasing debt massively reduced economic growth. This became a popular piece of evidence for fiscal conservatives to argue for reducing government spending, which was a major pillar of Mitt Romney's campaign. However, although Reinhardt and Rogoff published this finding, they did not publish their original data or analyses that led them to this result. Fast forward a couple of years, and Obama had won a hard-fought second term, but this scientific result was still out there, and a graduate student at the University of Massachusetts Amherst tried to reproduce Reinhardt and Rogoff's graphs for their homework for one of his classes. But he could not seem to get the same result. Although Reinhardt and Rogoff found that debt seemed to massively slow economic growth, Herndon kept on finding that debt seemed to have much less effect on growth. Now, as you might imagine, when it's your work as a young student versus two famous Harvard professors, you might naturally think that you're the one who's made the mistake. So Herndon wrote to those guys, and they sent him their original Excel spreadsheet. And it turned out that they'd made a number of errors in their original analyses. In other words, this major finding that had nearly changed the result of a presidential election was based on a flawed analysis. In this class, we're going to learn to analyze data in ways that minimize the chance of these errors happening. I want to quickly introduce you to the tools that we'll be using to accomplish that this semester. First, instead of using spreadsheet software like Excel, we will be analyzing data using a programming language called R. Whereas the actual analysis in Excel is hidden away in invisible formulae, R code is right out there with the end result. As you can see from the example on this slide, we can see the code and results side by side, which makes it easy to see if we have made a mistake. Now, R is a relatively old programming language, and in some ways it is a little dated. We will be using a group of extensions to R called the tidyverse, which allow us to analyze data using more modern methods that have been developed after R was first created. We will also be writing our R code in a program called RStudio. We will be using the server version of this program, which you can run through a web browser from any computer. RStudio gives you a single place to write code, run it, manage files, and do much, much more. It's an incredibly powerful tool, and it's one of the things that makes R so great for data analysis. If you have done any programming before, you might already be familiar with GitHub. GitHub is a website where you can publish code and share it with the world. Other programmers and scientists can then download your work and run it on their own computer. It's a great way to make your work reproducible by others. The final tool I want to mention is R Markdown. Markdown is a markup language, which means that it is a way of indicating how plain text should be formatted. It's common on the internet, where it's used by websites such as Reddit for formatting posts, so you may well have used it before. R Markdown is an extension of Markdown that allows you to intersperse R code with regular text. When you convert this into a final document, the R code will be run, and the output will be inserted into the document. This will make our analyses very reproducible, and we'll be looking a lot more at R Markdown in our first proper assignment.